Well, welcome everybody. We're going to have a fun 7 hours together, and we'll just get started. Let's see if I can use my computer here. Okay, Professor Law did a really nice job introducing me, but just in case that wasn't going to be there, I put together this quick slide describing my path. I think it's important as you look at people just to see how they got to where they are. I always wondered when I was, in places like you are now. So I'm originally from Central Connecticut, which is equidistant between Boston and New York. For the record, I am a Red Sox fan. Yankees suck. I did undergrad at MIT in aerospace engineering. I technically have a degree in aeronautics. And then I did both my master's and PhD at Georgia Tech with Tim Lewin. He was and still is an incredible advisor and a mentor that I am very proud to have. But he's also a big name and a very prolific researcher. And knowing that I wanted to go into academia myself, I felt like I needed to diversify a little bit. And so I did a short postdoc at Sandia, a year and a half, doing work in diesel engine combustion, which is completely different than what I did my PhD on. But it was very educational, and then went to Penn State. So I've been there since 2013. I recently just finished a sabbatical at the Electric Power Research Institute in Charlotte, North Carolina, which was very fun, working on something completely different. So that's me. My group, so this is kind of me professionally. I operate the Reacting Flow Dynamics Lab, and we work in three main areas. The first is combustor operability, which combustion instability is part of. And so that's what I did my PhD in, and that's, we will always continue to do that type of work, I think. But we have two areas that we've grown into. One is in alternative fuels. Putting a picture of hydrogen flames is not super exciting on a slide, but we do a bunch of work in hydrogen. We do some work in jet fuels, particularly sooting. And then I have a fun project on solid fuels that are biomass-based, and that's what that other picture is. But then our new area and our most rapidly growing area is in materials and durability, looking at radiative heat transfer in combustors, and particularly ceramic components, thermal barrier coatings, and ceramic matrix composites. So that's what my group does. But before we go on, I want to hear who you are. And this is both because like Professor Law said, I'm a graduate of the program. I'm very excited to be here as an alumna. But also, I'm very curious to hear what you all are studying and where you're from, so that it gives me a little bit of context as to how I'm going to give this lecture. But because there are 40 of you and just one of me, we're going to do this rapid style. And so if you could yell out your name, your institution, and then I sort of wrote this specifically for a grad student, but if you're not a grad student and you're either a postdoc or a professional, you can say what your work is, not necessarily your thesis work, but encapsulate your work in just 2 words. And so if this was me as a grad student, I would have said Jackie O'Connor, Georgia Tech, combustion instability. So we're just going to go around the room. We're going to start on top left. I guess that's you, man. Go for it.
Hi, my name is Nicolás. I'm from Chile. Institution is Universidad Técnica Federico Santa María. My thesis work is particle image velocimetry.
Awesome.
I'm Benny. I'm from University of Southern California, and I work on quasi-2D.
Awesome.
Hi, my name is Shojit Roy. I'm from University of Maryland. My work is on cold diffusion films.
Cool.
Hi, my name is Reese Churchill. I'm at Colorado State University, and I work on experiments and computations of alternative fuels.
Cool.
Hi all, my name is Parneet Lokini. I'm also from Colorado State University. I work in plasma-aided combustion.
Peter, University of Southeastern Norway, deflagration to detonation transition.
Hi, John, Columbia University, fundamental kinetics.
Excellent. We missed the back row. You guys want to go?
Yeah, Philip, I'm from Princeton, and I'm working on multi-component droplet combustion.
Cool. Awesome. All right, next row down.
Xiao from KAUST. I'm working on simulations of plasma-assisted combustion.
Cool.
Hello, Zainab, also from KAUST, and I'm working on diagnostics for hydrogen combustion.
Hi, I'm Juan from KAUST. I'm working on a control of thermoacoustic instability.
All right, we've got one thermoacoustician so far. This is good.
Hi, I'm Shiva from University of Utah. I'm working on Wi-Fi.
Awesome.
Islam from our National Lab, areas of gas turbine combustors.
Cool. All right, two thermoacousticians.
I'm John from MIT. I'm working on combustion kinematics.
Jared from University of Notre Dame, doing combustion CFD.
I'm Shonan. I'm from we start my technique in institute. I focus on the natural gas leakage monitoring.
Interesting. Okay.
I'm Trevor. I'm from Princeton, and I do numerical methods.
Cool.
Izzy, Princeton University. I do manifold modeling.
Michael, Princeton, flame annihilation.
I'm John. I'm at Princeton, and I do supersonic combustion.
Katie, also Princeton, and distributed combustion.
All right, so this is like the Mueller row, is what I'm hearing. Okay, great.
I'm Trevor from someone from University of Illinois Champaign, working on machine learning for LEDs.
I'm Josh Doblack from the University of Notre Dame. I work on propulsion systems.
Siva, I am from Universidad Politécnica de Madrid. I work on droplet combustion detonation.
Cool.
Behlul Nawaz, University of Massachusetts, Lowell, intrinsic instabilities.
All right, third instability person.
Duran, I'm from Technology Innovation Institute, UAE, liquid propulsion.
My name is Sai Walafai. I'm from the University of Illinois at Champaign, and I'm studying bubble bursting.
My name is Jakub. I'm pursuing my PhD in Building Research Institute in Poland and Hong Kong University in China. I'm doing tunnel pipes.
Cool.
Hugo from the University of Orléans in France, and I'm doing aluminum combustion.
UC San Diego, combustion instability.
All right, four.
So I'm Ahmed Barin. I am from Michigan State. I work in hydrogen combustion. The thing is measurement.
Awesome.
Roger Lucetta, Defense Threat Reduction Agency, Hazmat Combustion.
Excellent. Okay, thank you all so much. I know you probably weren't planning on being part of this, but this is going to be an interactive few hours here. So what I heard was we have 4 formal thermoacousticians and some people who probably play around the edges, which is okay, which makes me feel a lot better because in developing this set of lectures, I did not assume anybody knew anything about combustion instability. So for the 4 of you, this will be a nice review of some certain things. Hopefully will also be some new things as well, but for most of you, this will be new. Okay, cool. So if you get any formal training before you become a professor in how to teach people, which I did not until very far into my career, the first thing you should do when you create a class is write your learning objectives. And so by the end of this course, students should be able to do 5 things. 1, just talk about combustion instability, particularly in the technologies that it's a problem in, and we'll bring back these concepts to technologies as we go through. Describe the basic thermoacoustic coupling process. Explain the kinematics of flame response. And this is the big one. And we have a craft project that's going to go with this. So there will be some hands-on part of this. But this is the piece that I find is missing the most, where theory can provide the most insight, and I think is really the most critical part of understanding thermoacoustics is the kinematics of flame response. So we're going to talk about that a bunch. And then use that to assess the flame transfer function, to identify potential coupling processes, and then use your understanding of flame response and thermoacoustic coupling to explain instability control techniques, which is what we'll talk about tomorrow. So by the end of this, we'll be able to do all these things, yeah, hopefully this is a good fundamental understanding of thermoacoustics as a result. I put together a schedule, but I did not realize that there were like coffee breaks, so we can just ignore the schedule. And at 3 o'clock and 4:15, we'll take a break and grab some caffeine. I just made this up without knowing that there were breaks. So anyway, we're going to start though with just a quick introduction and then talk about the technologies before we start to dive into the theory. All right, so combustion instability comes in a number of different names. You'll hear people refer to it as combustion instability, combustion dynamics, thermoacoustics. I work with a company that calls them combustion oscillations. But whatever you call it, it's one of the most expensive problems in several industries. This is particularly true for gas turbines, particularly land-based, though increasingly aviation, and we'll talk about why as we go through. Certainly for rockets, and even for big industrial systems, including boilers and package furnaces. And I have an example of that. So you can't give a good thermoacoustics lecture without showing a picture of some destroyed hardware. So this is from looks like a F-class gas turbine, E-class maybe. There used to be a liner. You can see like the remnants of it here. These are the 5 fuel injectors. And this is what happened after a flashback event that was instigated by a thermoacoustic instability. So the thermoacoustics didn't do this itself. It caused flashback. The flame sat in the premixer for a really long time and led to a can being completely destroyed. Similarly, this is a picture. These are both gas turbine technologies because that's really the technology family that I tend to work in. But this is first stage turbine rotor. Each of these blades are like $25,000, and so now they're not anymore. This was due to a blow-off plus like high cycle fatigue issue. Again, a combustion instability issue. Very infrequently do instabilities get this bad, right? We're bad engineers if we let this happen regularly. We just like to show these pictures at the beginning for shock value. But mostly, so that's the damaged, expensive hardware part. The most important part is the reduces operability, and this is actually why it's so expensive. One of the things we'll see is that there are going to be these islands in which instability appears in your operating map. And so what you end up doing if you have to operate one of these devices is sort of play this weird game of hopscotch around those islands. And if you're running a business like a utility or a power plant or something that's very low margin, profit margin, or if you have a rocket which has like 2 settings on and off, that's really problematic if you have the complexity that's added when you have to sort of hopscotch around these islands. And so many of the biggest issues come on the operability piece. The final part of it, particularly for low NOx technologies like gas turbines, aircraft engines, and industrial systems, you probably did a lot of work as a combustion engineer to get these to be low NOx technologies. But the problem is that when you did that, you made the flame inherently less stable, and so when it goes into an instability mode, it creates hot pockets that just produce all that NOx anyway. So, all that work you did is just negated by the instability. So these are reasons, in addition to the threat of absolute destruction, that we want to avoid instability issues. One other thing I'll say before I keep going, I'd like this to be interactive and informal. So if you have any questions at any point, just raise your hand. Super happy to talk through things. I get a little bit nervous if I'm the only person talking for a whole hour. Okay, all right, so thermoacoustic instability can basically happen anytime you put a flame in a chamber. And so, there are examples of this. We're going to talk about this engine right here. This is the F1. Gas turbines, package boilers, but even water heaters. So gas-fed water heaters can have combustion instability issues, particularly as the age and the hardware changes, or if the composition of your natural gas changes significantly. When I was a student at Georgia Tech, there was always an experiment. It wasn't in my group, it was in Professor Zinn's group, but there was always just a set of water heaters in the corner that were constantly getting tested. And so, you know, from the mighty F1 to the lowly water heater in your basement, it's really the same types of problems that are driving these instabilities. So let's look at a couple motivating examples, and then we'll get into the actual physics here. So let's start with the F1. The absolute best reference on this was a paper written by two of my favorite people, Joe O'Flynn and Vigor Yang, when Joe was a PhD student at Penn State. Vigor's now at Georgia Tech, as is Joe, actually. But they were originally from Penn State. And they wrote this really nice history article for the Journal of Propulsion and Power, talking about the development of the F1 engine. So the F1 was the engine that went on the Saturn V, so there were 5 F1s that powered the Saturn V to go to the moon. And there were about 3,500 fired tests of the entire engine in its development cycle. About 2,500 of those were to get rid of instabilities. You can imagine, let's go back to this picture, how humongous this engine is. And if you're firing that off thousands of times to get rid of instabilities, that gets very expensive very quickly. So this, let me see. So this is the instability that they saw. And so here you can see on this plot, this is 10 milliseconds here. But what I really want you to look at is the size of the graph paper here in the Y direction. So this is the combustion chamber pressure. So in a rocket engine, this is the injector head, and we'll see pictures of the injector head in just a second. And then combustion is here, and then you have the throat and then the nozzle that accelerates the products of combustion and provides the push for the propulsion. So this is the pressure measured in here, and they don't give you the mean, but they do give you the fluctuation. And so these fluctuations are about 2 boxes tall, and each box is 500 psi. This is like, I don't know, almost 70 atmospheres peak to peak. That's insane. That's insane, right? Just think about the mechanical stresses on this part as the pressure is swinging by 70 atmospheres up and down. There are some, this typically doesn't, this was a liquid-fueled rocket. I've heard of solid rockets, which we won't really talk about in this class, but in solid rockets, I've heard that instabilities have been so dramatic that they've drawn a vacuum on the system. So in rockets, these instabilities can be extremely powerful and can do some serious damage, which is what happened. So this is what one of the injector heads looks like. So this is the original injector head. So they have thousands of these little injectors. They're these coaxial injectors. I know the pictures are a little bit hard to see. This was published in the era before digital publishing. But when they first built it, they just had all these rings of injectors, and they did a really nice job thinking about the mixing and where the flame was going to sit or whatever. And it looked like this. But then as they started to have these instabilities, they put a bunch of pressure measurements on and realized that the acoustic modes, which we'll talk about, were actually running around circumferentially and radially inside the combustion chamber. And so what they did was they put on a series of baffles. And so these things are called baffles. They're literally just, so for the F1, you know, this entire thing is about 4 or 5 feet across. The baffles are like 4 to 6 inches tall. And what they were trying to do was break up the acoustic mode to stop it from oscillating in the circumferential and in the radial direction. They did not, however, have any simulation capability, and the theory on this was really quite new. And so a lot of these tests, and this paper talks about this in detail, a lot of these tests were kind of guess and check to see if these shapes were going to work or not, which is why they had to do so many. Eventually they got it to work, and we went to the moon, and it was great. But in the meantime, we learned a lot about thermoacoustic instabilities from the F1 development, and I highly recommend this paper if you're interested in that. All right, this is still an issue on rockets. I kind of cringe every time one of these space startup companies says, yeah, we're going to build our own rocket engine. We can totally do it. I'm like, oof, they're going to run into this. Hopefully they have some good engineers. Okay, second application, and this is really my home application. So this is an example from a book I really like. So shameless plug for academic parents' book. This is an edited volume called Combustion Instabilities in Gas Turbine Engines. It was edited by Tim Lewin and Vigor Yang. But the thing I really love about this book, there's, sections on physics and control and modeling and all of that. But the first section is user experience. Somehow Tim and Vigor got like 8 different companies to air their dirty laundry and talk about all the problems that they were having in their engines with instabilities, what they did to control it, and test it and monitor it. It's absolutely fascinating. It's required reading for all the students in my group who do thermoacoustics. And so this is a particular chapter from Rolls-Royce. Rolls-Royce has a series of aeroderivatives. They have since sold the aeroderivative business. It doesn't really matter. But this is what it looks like. So they took the turbo machinery from a Trent aircraft engine. They replaced the combustor with this weird, it's called a siloed combustor. One of the nice things about a silo combustor is you can put in fuel injection in a bunch of different places. And so this actually has 3 injection ports. They really only start playing around with 2. So there's what they call the primary premixer and the secondary premixer. And depending on what power you need for the engine, you go through these different operating maps, right? So this is the operating regime for 80% power, and this is the operating regime for 100% power. So remember, this is the operating map. This is what the machine can do without blowing off or flashing back. But within this operating map, they have these regions of thermoacoustic instability. And so this is a similar plot. Here, these are different power levels and the primary circuit temperature. And you can see the noise amplitude at different powers. And so as you increase in power, depending on how much fuel you're putting through this primary premixer, you can actually get some pretty significant instabilities as a result. So one of the things they talk about in this is how they redesigned the premixer geometry and actually got the instability to go down significantly. So this is noise amplitude as a function of load. Here they have the original premixers. They did some design changes and they got it to be a lot quieter. So a few takeaways from this. One, where you put your fuel and where you put your flame seems to matter a lot for the instability, and we'll see that. And some nifty aerodynamic design can help suppress the instability, and we'll also see why as we go through and talk about the theory. Okay, so this also happens in industrial systems, but industrial systems are really interesting. So this example is from a paper that I collaborated on with a bunch of folks from Babcock and Wilcox. They're one of the largest manufacturers of package boilers and industrial systems in the US. And then a group, Chuck Finney and a couple other folks from Oak Ridge who do modeling of this system. Myself and then a colleague of mine at Penn State, Tyler Dare. And so here we were looking at package boiler systems. In particular, the system that Tyler and I were analyzing for the case study that we did for this particular paper is a paper plant in central Pennsylvania. And they have a huge boiler system that goes to heat up the pulp before it gets made into paper. And so you have, I don't know if you're familiar with these types of systems, but you have air that comes into what's called a wind box. You can think of this as basically just a settling chamber. And then you mix the fuel in the burner, and there's a furnace here, very long flames, and then the generating bank is basically a big heat exchanger, and then air comes out the boiler outlet. And so this thing is humongous, right? So this is what, the average size of one of these things, and that's a person. So these are really, really big, which means that their instability frequencies are very, very low. This was some data that Tyler took on the system itself. All these numbers are accelerometers that he put on the system. because it was the reason they knew this was happening. The instability frequency was like 10 hertz or something, which you can't hear, but you can see the panel on the side of the boiler moving. And so they were like, well, that's not good. And so they had him come in and instrument it. And you can see for a bunch of these cases, they were changing a bunch of stuff about how air was flowing through the system, and they could excite the instability or dampen it. And in my group, we did a bunch of modeling to help identify the regions that were most sensitive. This is just an acoustic simulation of the system. And you know, the instability or the eigenvalue frequency of like 9.5 hertz, which matched pretty closely to the instability frequency they saw in the system. So fortunately, these systems are pretty modular, so there are a lot of things that you can change in order to damp the instability. But again, they're actually pretty complex just because they're so humongous. And so this type of modeling really helped identify where they should start playing around with things at different operating conditions to suppress the instability. All right, so hopefully this gives you an idea of the type of problems that we're looking at, all different types of systems. I didn't have a good water heater example, so we'll just end it there. But now we're really going to dive in, and for the rest of today, we're going to talk about the feedback process, and then flame kinematics, and how that drives the feedback process before tomorrow we start talking about how we quantify this and actually control it. Any questions before we move on? Yeah?
So when we talk about you mentioned the F1 engine had instabilities going around the circumference. So is that any way related to RDEs in a sense, or is that?
This is a really good question. So for folks who couldn't hear the question, he asked, you know, this circumferential mode, is it anything like an RDE? And the answer is no, because that's a detonation, and this was just an acoustic wave. And I'll show in some really terrible PowerPoint art what this looks like in just a sec. But RDEs, you know, have the flame front following the acoustic wave, and here the acoustic wave is interacting with the flame differently. That said, a lot of people who do thermoacoustics looked at RDEs and were like, we got that. Because a lot of the particularly injector dynamics problems that you see on RDEs are exactly the same thing that you see in these circumferential modes in other technologies like rockets or gas turbines. And actually, when we talk, the last thing tomorrow afternoon, one of our advanced topics, we're going to talk about transverse modes, and we'll come back to exactly that.
So it's more than just an amplitude difference, but there's also a general physical difference.
It's a fundamentally different physical process, but the acoustic driving of some of the injector problems is actually pretty similar. So a lot of the knowledge is transferable. Great question. Other questions? No stupid questions in my class, or there are no stupid questions in my class. I am the queen of asking questions that I'm pretty sure are going to make me look like an idiot, but I want to know. It's a good skill to develop. Okay, good stuff. All right, so I went a little nuts. Usually I don't teach on PowerPoint, and you guys are going to see why, because I went a little nuts with the slide designer. So every once in a while, we're going to have these sidebars, because I need to teach you a few things that don't fit in super well with the flow, but you're going to need to know. And the first thing is some basic acoustics. And so this is the part where I'm going to do it on the board. We're going to see if this works. Yeah. All right. Cool. If I write big, are folks going to be able to see this? We'll see. Okay. So acoustics is a wave propagation, and mostly I did this on the board because I hate writing equations in PowerPoint. Just put it out there. All right. So acoustics is a wave phenomenon. Does anybody know what a wave is? Thermoacoustics people can't answer this because you should know what a wave is. Anybody who doesn't do thermoacoustics professionally know what a wave is. It's a tricky question.
Periodic signal.
Okay, there's some periodicity. Usually. Doesn't have to be, though. Yeah?
Is it related to information transfer?
Ah, there's a transfer. That's pretty key.
Harmonic.
So that goes with periodic. Doesn't have to be harmonic. Any other thoughts? These are all good. Let's go with this transfer idea. So a wave is a transfer of energy without a transfer of mass. So if I threw you a hot potato, I am transferring energy, but the potato has a mass, and so that's not a wave. But I'm yelling at you right now. You're not, like, catching anything, right? This sound is getting to you because of a transfer of energy through a medium without any transfer of mass. And so when so waves can be periodic, and often they are, but they don't have to be, right? I could pop a balloon, right? And that's an impulse, and that impulse could travel to you as a wave, and then it would just be silent afterwards, right? So this is sometimes, but this is the definition up here. When you first learn about waves, where was the first place you learned about waves? Other than the beach?
Lights.
Yeah, probably electricity and magnetism, right? Everybody's favorite freshman course. And so you remember there was this thing called the pointing vector, which is the direction in which the wave was moving. And then you'll notice I'm going to be a terrible artist. And then the E wave was doing one of these. And then the M wave, oh God, was coming out of the page. And they're all going in an opposite direction, right? This is called a transverse wave. Because the oscillations in the energy are oscillating transverse to the direction of motion, that pointing vector. Acoustic waves are different, though. They oscillate in the direction of motion. And so the opposite of, or not opposite, the other one is called a longitudinal wave. And honestly, the best way to describe this is using a slinky. So I own a lot of slinkies because of this. And I have a slinky that I can pass around if you want to play with it. We had 2 at home, and I packed one, and my husband was like, what am I going to do with this extra slinky? You should bring a second slinky. So. Okay, slinky for you. You can play around with this. Okay, so I don't know how this is going to work without a table. Usually I have a table. But if you stretched out the slinky, so imagine that each of the rings of the slinky here is a pressure isobar, right? And so when the slinky, pretend it's not moving, when the slinky's at rest and there's no wave going through, they're all evenly spaced, and so we have a constant pressure field here. But as I, provide some impulse to the edge of the slinky, what ends up happening is locally the slinky is compressing and then expanding, and then locally compressing and then expanding. And so this oscillatory motion, if I was going to draw a longitudinal wave, it would look like high pressure, low pressure, high pressure, low pressure as the wave traveled. So it's this kind of weird compressive motion as you go along the direction of travel. Does that make sense? You keep passing around the slinkies. I'm going to throw the slinky to you. Ready? Okay. All right. So if I think about physically what's happening here, I think we all have in our heads that acoustic waves are pressure waves. And so I have some pressure fluctuation here. If I assume that my gas is ideal, which is a good assumption for many gases, I can say that my pressure is equal to my density times some particular gas constant times the temperature. If I assume that I'm not changing the composition of my gas, so that's a constant number, then having some P prime will also lead to fluctuations in density and temperature. And you can see that as well. Now, if you think through it, if I'm varying the pressure and the density of a fluid as this wave travels through, I'm probably also varying the velocity of the molecules as the wave passes through. And so that's very much what ends up happening. In this class, I'm going to use lowercase u as our velocity. And so what ends up happening as you go through is you not only have variations in the pressure, so you have high pressure when all the wave goes through and compresses all the molecules together. There you have low velocity because everything's getting squished together. And then as these expand out, the velocity, this is a fluctuating velocity, right? This isn't a mean velocity because we don't have any mass transfer, right? If we had a mean velocity, we'd have mass transfer. Where was it going? Oh, so you have a low velocity at the high pressure and a high velocity at the low pressure where you have the expansion in between, right? And so if you want to talk about an acoustic wave, you can talk about fluctuations in pressure, fluctuations in acoustic velocity, and we'll get back to what I mean by that in a little bit, and then similarly, fluctuations in density and temperature. Questions on that? Okay, important side note. There's actually an interesting experiment or science story that goes with this. We assume that sound travels isentropically. So sound propagates isentropically, at least in the linear regime. When sound gets nonlinear, all of this kind of breaks down. You can have what's called acoustic streaming, where you get a mean velocity because of acoustic forcing. You get shock propagation, right? None of that is linear or isentropic. But in a linear regime, sound propagates isentropically, and if you do a bunch of math, which I'm not going to do, you can show that the sound speed, which I'm going to call c, is equal to gamma RT, where gamma is the ratio of specific heats, right? So this is Cp over Cv. R is the particular gas constant, and T is the temperature. Initially, scientists, there's probably some like Count something, Baron whatever, doing science in his backyard. But initially they thought sound propagated isothermally. And if you do that, you get a very different equation for the sound speed. And so they were measuring like depth charges and the sound produced by them in lakes. They just kept getting the wrong number and they didn't understand why. And then somebody, and I forgot his name, I should know it, realized, oh, this isn't an isothermal propagation, this is an isentropic propagation. When you do that, he got the sound speed pretty much perfectly. And so this is an equation that's going to come back to us a few times as we go through. A good number to remember, at standard temperature and pressure in air, C is 340 meters per second. Just like one of those numbers that's good to remember. Okay, so this is sound propagation. Questions on propagation before we start looking at waveforms? Yeah?
Can you repeat what's meant by linear? What's linear between isentropic propagation?
I am very glad you said that because this concept of linear is going to come up a lot. Okay, so for the purposes of this series of lectures. Linear means that your perturbations are small, and so linear math works, essentially. So if you have, you know, there are a bunch of different ways that this conversation could go, and I'm just trying to make sure we're talking about it in the most useful way right now. Basically, you know, you have additive properties in linear systems, right? You have those sorts of things. But for the purposes of this work, what we're saying is that the amplitude of the disturbance is small, such that you can describe the relationship between the outputs and the inputs in a linear way. Does that make sense? Yeah?
It's just saying there are no shocks.
Not necessarily, because you can get to nonlinear waveforms before you get shocks. Actually pretty easily. And we'll see some examples of that, hopefully, if we have enough time tomorrow. But if you, for example, a nonlinear process in acoustics is harmonic generation, right? And so if I have a speaker and I give that speaker just one sine wave, like produce sound at 200 hertz, and if all that comes out of the speaker is sound at 200 hertz, that's in the linear regime. If you force it too hard, what comes out is 200 hertz and 400 hertz and 600 hertz. Those are the first and second harmonics. That's a nonlinear process without having a shock. Did I see a hand over here? No? Okay, cool. All right, so that's propagation. So now let's talk about what the waveforms end up looking like. So I'm not going to go through and do the derivation. One could do that for fun at home. But because this is a wave, it follows or behaves per the wave equation, which again is probably something that is stored in memory somewhere from E&M. But in acoustics, we write it in terms of pressure. So it looks like this. And so basically this is, the solution to this describes the propagation of acoustic waves without any forcing, right? So if you had a speaker or some sort of source, you could put that term over here. But basically this just says that we have oscillations in both space and time as we go through and look at this. The solution to this equation, we're just going to look at the solution in 1D. I don't want to go too nuts, so I'm going to rewrite this in one dimension quickly. Whoops. You can tell I've been on sabbatical for a year because my chalkboard technique is worse than it usually is. Okay, so now we're looking at a situation here where we have propagation in just one direction, the x direction, and then oscillations in both space and time. And the solution to a wave equation like this ends up generally looking like, plus g of c minus x. Basically what this says is you can have waves that travel backwards and forwards in space and that propagate forwards in time, because we can't go back in time. We could get philosophical as to why. And so this is the general form of this equation, or this solution. You can put a bunch of different functional forms in here that work, but the ones that we're going to focus on for the purposes of the lectures this week are harmonic functions, right? So one of the solutions to this is sine waves, right? I don't know about you, but one of my least favorite things in math were the trigonometric functions. Anybody enjoy trigonometric identities? Ugh. It was one of those things in algebra that you did and then you just immediately forgot, and this is what Wikipedia is for. Fortunately, math has an easier way of dealing with this, and this is called the Euler identity, so that you don't have to remember what sine of omega t times cosine of omega t actually is. you can just say that e to the I omega is, whoops, cosine, sorry, that's a theta, plus I sine theta, where I is the imaginary number. Show of hands, who's worked in complex exponentials before? All right, half of folks, that's okay. They work just like complex numbers and exponentials. So everything you remember about the imaginary number works. It's just a way easier way of doing the math because exponential identities are pretty easy to remember, whereas, like I said, I don't really remember my trigonometric identities. So as a result, if I know sine waves are a solution to this, and I get lazy and I don't want to do all the sine waves, I can write the solution in this way instead. What you end up with is a solution that looks like the following. When you work in complex exponentials, the very last thing you have to do is take the real part because the world works in real numbers. But you end up with the real part of p plus e to the ikx plus p minus e to the negative ikx times e to negative I omega t. So basically what this equation is saying is I have a forward traveling wave, I have a backward traveling wave, and I have an oscillation in time. I have made some decisions about where the minus signs go in my exponents. How you do that is referred to as the branch cut. I have unreasonably strong feelings about this branch cut because I don't mind the minus sign in front of here, and I want my forward traveling wave to have a positive sign and my negative backwards traveling wave to have a negative sign. But you could flip all the signs of those exponents and have the exact same solution. And half the acoustics books out there write it this way and the other half write it the other way. And it's supremely confusing when you're first starting acoustics. What makes this easier, however, is the fact that we almost never deal in acoustics with this partial differential equation, because why? Instead, we take the Fourier transform of everything and do it in the frequency domain. Because like you saw in those motivating examples, we want to do things at particular frequencies anyway. You'll see why when we get to the thermoacoustic feedback process. And so next thing I'm going to do is I'm going to take the Fourier transform of this equation, which is going to give me something that looks like this. I'm going to call my Fourier transforms hats. So this is x squared plus k squared p hat is equal to 0, where k is equal to omega over c, and omega is equal to 2 pi times the frequency, so that's the angular frequency. So what happened here is when I took the Fourier transform of a second derivative, in time, the Fourier transform of a single derivative in time is I omega. I ended up with I omega squared. That's where this negative sign went. And then omega over c, it was omega squared over c squared gives me k squared. And that's where that went. And now, this is an ordinary differential equation, which is way easier to deal with. And so, if I'm now going to write my expression for p hat, which is now at a particular frequency, this is just equal to p plus e to the ikx plus p minus e to the ikx, negative ikx. The p plus and p minus are the amplitudes of the forward and backward traveling wave, and k is that wave number omega over c, which is kind of like a frequency but for space. Okay, so those are the solutions that we end up getting from there. And we're going to see these equations a couple more times as we go through, so I just wanted to introduce them initially. Questions on this?
Can you restate what p hat was?
Yeah, this is the Fourier transform
Of p?
of p. Well, it's the Fourier transform of the entire equation. But yeah, p hat is the Fourier transform of p. And also remember, going back to complex exponentials, p hat is a complex number. Right? Fourier, things in the Fourier space are complex. I can rewrite this complex number, a plus ib, as a times e to the I theta, going back to Euler. Where'd he go? It's right here. Such that big A is equal to the square root of little a plus little b squared, and theta is inverse tangent of b over a. Okay. For those of you who haven't seen complex analysis in a while, this is good stuff. Cool. Any other questions? Yeah.
Okay, you Fourier transformed on time, not Fourier transformed on space.
Yes. Yeah. Yep. Because what I really want to do, I want to do everything in the frequency space, and that's, yeah. You could Fourier transform on space, but it's not as helpful.
Doesn't do anything for you.
Yeah.
So what would be a way to understand what p hat represents, like the way to conceptualize it?
We're going to get to a whole bunch of that. So p hat is basically just the, it has the frequency information of a particular time signal. So maybe if folks are not familiar with Fourier transforms, that's totally okay. Maybe at the break we can do a quick sidebar on that. But p hat gives you the amplitude and phase. So we call this A the amplitude and theta the phase of the oscillation at a particular frequency. Okay, cool. So the reason we're going through all this headache is because you'll see in just a bit, the thermoacoustic feedback loop relies on sound waves, right? That's half of the feedback loop. But in particular, one of the things that's typically happening is that sound waves are resonating inside a particular chamber. So remember I said anytime you put a flame in a chamber, you could have combustion instability. You won't necessarily, but you could. And what's happening, and we'll go into much detail in a bit, is that you have some coupling between the resonant mode, which looks like this, and the flame. So I just want to say one quick thing on resonance, and then we'll go back and look at a couple pictures, and then we'll hopefully have enough information to talk about the feedback loop here. So resonance is, this is my little resonance box. Resonance is a constructive feedback process. So imagine the way I describe this when I teach this is a string, right? If I had or a jump rope. If I had a friend over there, I should have brought a jump rope and gotten a friend, but you can move the jump rope together such that the whole jump rope moves up and down, right? And if you're really fancy, one of you can go up and the other one can go down, and you can get the jump rope, to do kind of a half and half thing. But if you and your friend are just randomly wobbling it on each side, the jump rope's not really going to look like anything coherent, because there isn't constructive interference between your oscillations. What you and your friend are doing, and 8-year-olds seem to be able to figure this out intuitively, is you are moving together such that the waves you're generating on each side are constructively interfering. They're adding together such that you get this nice coherent motion in the jump rope. The same thing happens when you have acoustics. And so in order to be able to talk about this, we need to define one more thing, which is the wavelength. So the wavelength, we give it the symbol lambda, is equal to the speed at which the wave propagates times its frequency. So you could just do quick dimensional analysis. This is in meters, and this is meters. Wait, Did I do this backwards?
Isn't it
Yeah.
velocity equals frequency times wavelength?
Yes. Should not try to change my notes on the fly. Okay, so now this is meters per second is equal to meters times per second. So then we get lambda is C over F. So this is if I have a particular length jump rope or combustion chamber or whatever, that's the wavelength, and I know what C is because I know what's inside there, right? So I know gamma, R, and T. I can tell you what the resonant frequency would be, and if you have some source of oscillation that's at that frequency, those waves will constructively interfere and basically amplify themselves until you get a resonance. It's also the frequency at which things naturally resonate. So if you've ever like kicked a pipe or what's another good example? I would say blow over a Coke bottle, but that's a slightly different process. Either way, systems have this natural frequency, and it has to do, it's dependent on the sound speed, and it has to do with how the acoustic wave sort of fits inside that shape. Okay, now what do those resonances look like? So before we go to the break, I'm gonna go back to the board. Okay. Gonna take a while. Should have planned for this. You can do it. This worked last time. There it is. Okay, great. And so you can see now the way that I've drawn this, I have some velocity oscillation, some acoustic velocity oscillation, and I have some pressure oscillation inside this tube. And the wavelength of the oscillation fits inside the tube. And so depending if this is the wavelength and I have the speed of sound, I can calculate the frequency of this wave. This is the longitudinal mode, and this is kind of the easiest to visualize. Unfortunately, a lot of combustion chambers are round, and the math for round systems is difficult. What's called the azimuthal or circumferential mode also oscillates harmonically, so sines and cosines. But the radial mode is actually described by a series of Bessel functions, which sort of hurt my brain the first time I learned them. So we won't go into the mathematical description of these modes. But either way, the same idea fits, right? That you have this oscillation, it has some mode shape that's determined by the solution, and it fits inside the shape and oscillates at the frequency, which is determined by the speed of sound. Okay, and that brings us to 3 o'clock, and I want to take breaks seriously. So let's do 15 minutes, and then we'll come back and sidebar over, and we'll come back to thermoacoustics. If anybody wants to talk about Fourier transforms, I'd be super happy to do that down here, or we could all just get some coffee.